Welcome to the primary flight controls lesson in the PMDG 737 Next Generation Groundwork from Angle of Attack. This lesson will cover the following topics: general overview of an aircraft's three principal axes and the control surfaces that act on each one of them, basic physics of control surfaces, primary flight controls on the 737 NGX for pitch, roll, and yaw. We'll also be discussing their relationship with the hydraulic systems and the standby hydraulic system, horizontal stabilizer trim, flight spoilers and yaw damper, Mach trim system and speed trim system, 737 NG flight controls system components, and a lesson summary. An aircraft's attitude can be changed around three perpendicular axes that intersect at the center of gravity, or CG: lateral axis, longitudinal axis, and vertical axis. External forces like wind may alter the desired flight path, thus creating the need for the aircraft to be maneuvered back to the correct attitude through three movements: pitch around the lateral axis, roll around the longitudinal axis, or yaw around the vertical axis. To achieve these movements around the aircraft's axes, flight controls are employed. There are two groups of flight controls: primary and secondary. Secondary flight controls are covered in the secondary flight controls lesson. The primary flight control surfaces and their direct effects are elevators, change in pitch, ailerons, change in roll, or rudder, change in yaw. An aircraft is free to rotate within the three axes and will always turn about its CG, or center of gravity. The tendency to do this is known as a turning moment. A moment is equal to the product of the force applied and the distance from which the force is being applied. This is known as arm, and it's measured with reference to a defined datum. Because the relationship between force and arm is inversely proportional, the longer the distance from the datum means the force has to be smaller to maintain positive balance, and vice versa. The flight controls are designed to deflect airflow and produce these forces that make the aircraft turn around its axes. This is done by changing the angle of attack of the control surface, thus allowing for a change in lift. For example, when the control column is pulled back, the elevators are deflected upwards, and due to the lower angle of attack on the control surface, there is lesser lift in the horizontal stabilizer, causing it to go down and thus bringing the aircraft nose up. The 737 NG has two elevators, two ailerons, one rudder, and 8 flight spoilers. We'll now split this lesson into pitch, roll, and yaw. Elevators are movable surfaces attached to the rear spar on the trailing edge of the horizontal stabilizer that control the pitch attitude of the aircraft around its lateral axis. The pilot moves the control column forward or aft to achieve the desired change in attitude. Paired cables are used to transmit pilot input into the respective interfaces and flight control surfaces. In order to provide system redundancy, each hydraulic system, A and B, powers one of the two elevators on the 737 NGX. Either hydraulic system may power both elevators in case one of the two systems fails. The basic principle is the control column sends the pilot's inputs to the Elevator Power Control Unit, or PCU, which is an interface between the pilot's mechanical input and a series of hydraulic actuators on each elevator. These inputs are also sent to the Flight Data Acquisition Unit, or FDAU, for flight data recording. The autopilots have a separate series of actuators that also give mechanical input to the elevator PCUs. The right PCU gets hydraulic system B pressure, and the left PCU gets system A pressure. This means either hydraulic system may command both elevators in case one of the two systems fails. The PCUs ensure that the elevators may always be moved under any condition. This means that even in the event of a complete hydraulic failure, the cables and linkages allow for manual operation of the elevators. This condition is known as manual reversion. In case one of the control columns becomes jammed, elevator control is still achievable from the other control column thanks to the elevator breakout mechanism. This provides added reliability and system redundancy. At least 31 pounds of additional force must be applied to use the working control column while the other is jammed. In this condition, when 100 pounds of force are applied on the control column, the elevator moves 4 degrees. In a total hydraulic failure emergency situation, this amount of deflection is sufficient for a safe landing flare. The elevator PCUs also limit the amount of elevator travel. When the horizontal stabilizer is neutral and there's no input to the mock trim actuator, which will be discussed further along, the elevator is downrigged 4 degrees, with reference to the stabilizer mean chord line. From this position, the elevator can move 24.3 degrees up and 18.1 degrees down. Each elevator has 3 balance panels, with balance weights in the forward side and a tab attached to the aft edge. The balance panels decrease the force necessary to move the elevator in flight. The elevator feel and centering unit is a computer that gives variable control column forces as the airspeed changes and the horizontal stabilizer moves. The elevator feel computer receives input from pitot tubes through pitot ports, hydraulic system A and B, horizontal stabilizer, elevator feel shift module, or EFSM. This last mechanism operates during a stall, providing 850 psi of hydraulic system A pressure to the elevator feel system. Elevator feel and centering also moves the elevators to a neutral position when there's no input. When the control column moves, a roller is moved, causing springs to extend and provide a feel force. When the control column is released, the roller moves to a detent, and thus the system moves to a neutral position. At higher airspeeds, the elevator feel computer increases the metered pressure to the control column feel system to provide simulated aerodynamic forces when operating the control columns. This feature is not available during manual reversion. The elevators also have a tab that varies to help reduce the required elevator pitching moment. When the trailing edge flaps are up, the elevator tab operates in balance mode. The tab moves in a direction opposite to elevator travel. When the trailing edge flaps are not up and there is hydraulic power, the elevator tab operates in anti-balance mode. The tab moves in the same direction of elevator travel. Most aircraft have little surfaces on the flight controls that are utilized to hold the aircraft in its current attitude without the pilot having to make excessive input on the control systems. This process is known as trimming the aircraft, and the 737 NGX is trimmable in all 3 of the primary flight controls. The pitch trim is controlled with a movable horizontal stabilizer by any of 3 ways: manual operation with the stabilizer trim wheels, electric operation with the stabilizer trim switches, or autopilot operation, achieved electronically through a digital flight control system, or DFCS. During manual operation, the pilots use stabilizer trim wheels that are linked to a mechanism with a jack screw. When the jack screw moves, the horizontal stabilizer moves. It's good to know that under normal conditions, the stabilizer trim is the only control surface on the 737 NG that's completely independent from the need of hydraulic power. This also means that under certain flight conditions, the effort required to manually operate the stabilizer trim may be higher. During electric operation, the pilots operate 4 stabilizer trim switches located on the outboard side of each control wheel. These control electric input to the stabilizer trim actuator that also moves a mechanism with a jack screw. Like we mentioned before, when the jack screw moves, the stabilizer moves. The system is made so that when the electric stabilizer switch is operated, the horizontal stabilizer is moved, and so are the stabilizer trim wheels. In case the stabilizer is trimmed to the end of its electric limits, additional trim is available through the manual trim wheels. Finally, during autopilot operation, the digital flight control system gives electric input to the stabilizer trim actuator. However, this actuator operates at different speeds when receiving autopilot input. Stabilizer position sensors feed the DFCS. Sensor A sends information to the DCFS via the Flight Control Computer, FCC, A. And similarly for sensor B. There are various switches associated to stabilizer trim operation. Column cutout switches, stabilizer trim override switch, stabilizer trim cutout switches, flaps up switch, stabilizer trim limit switches. The column cutout switches allow for the stabilizer trim to stop in case the pilot electrically trims the stabilizer opposite to elevator control input. The stabilizer trim override switch bypasses the column cutout switch. The pilot uses this switch to operate the electric trim if both column cutout switches fail. The stabilizer trim cutout switches are used to stop the stabilizer trim actuator if there's any uncommanded motion of the trim actuator. The flaps up switch determines trim speed relative to flap position. When the flaps are up, low speed trim is engaged at 0.2 units per second. When flaps are not up, high speed trim is engaged at 0.4 units per second. The stabilizer trim limit switches limit the range of stabilizer travel. There are different limits for manual, autopilot, flaps up, or flaps down operation. There's also a takeoff warning switch that alerts for incorrect stabilizer trim configuration during takeoff. The cockpit stabilizer trim indicator has a green band to show the takeoff trim range. The horizontal stabilizer movement lower and higher limits, as well as the neutral position, are marked on the fuselage. The limits are 4.2 degrees of stabilizer leading edge up, 12.9 degrees of stabilizer leading edge down. It's good to keep in mind that when the stabilizer moves up, the aircraft nose moves down, and vice versa. We've mentioned the Mach trim system a couple of times during this lesson. This will be explained now. Mach number is the relationship between the true airspeed of an aircraft and speed of sound. If the Mach number exceeds 1, the aircraft becomes supersonic. The 737 NGX has a maximum cruising speed of Mach 0.780. The Mach trim system provides speed stability at Mach numbers above 0.615. Elevators are adjusted relative to stabilizer position as speed increases, subsequently changing the control column neutral position through the elevator feel and centering unit. The Mach information is obtained from the Air Data Inertial Reference Unit, or ADIRU. Another similar system in the 737 NGX is the speed trim system. Like the Mach trim system, the speed trim system also provides speed stability. However, it's designed to return the aircraft to a trimmed speed by trimming the stabilizer opposite to the direction of speed change. This also increases control column forces. Some conditions that have to be met for speed trim operation are low gross weight, aft center of gravity, N1 greater than 60% or high power settings, airspeed between 100 indicated knots and Mach 0.50, and autopilot disengaged. Essentially, when the speed trim system comes alive, it requires the pilot to provide a significant amount of pull force to reduce airspeed and significant amount of push force to increase airspeed. You can see that there are quite a few ways that the elevator controls translate to direct and comfortable pilot control. Although quite complex, this elevator system is relatively simple compared to other aircraft flight control systems. Ailerons are movable surfaces on both wing outboard trailing edges that control the flight attitude of the aircraft about the longitudinal axis, more commonly known as roll. The ailerons are coupled so that when one of them moves down, the other moves up. There are 3 ways of achieving roll control on the 737NG. Manually, by moving either control wheel, automatically, by autopilot input to move control wheels with actuators, or through flight spoilers. These will be discussed at a further stage during this lesson. During manual operation, the flight crew controls the roll attitude with control wheels that are interlinked mechanically in order to provide system redundancy. Just like with the elevators, the ailerons are actuated through pairs of cables that transmit force. Ailerons are also operated via the Aileron Power Control Unit, or PCU, that acts as an interface between the pilot's mechanical inputs and a series of hydraulic actuators that move the ailerons with wing cables. The aileron PCUs ensure that the ailerons are movable under any condition. Under normal operation, each hydraulic system controls a single aileron. In case of a hydraulic system failure, the working system may control both ailerons. In case of a total hydraulic failure, ailerons are still controllable mechanically. This condition is known as manual reversion. The upper PCU gets hydraulic system B pressure, and the lower PCU gets hydraulic system A pressure. The PCUs also limit aileron travel to 20 degrees up and 15 degrees down. When pilots turn the control wheels, mechanical stops in the aileron control wheel components keep the control wheel movement limited to 107.5 degrees left or right.